This is going to be the first of 3 lectures on the evolution of feeding behavior. Let's first talk about how animals acquire food. Well, the first thing you need to do is locate a potential food item. And there are different stimuli that animals can use to find their food. For example, if you're a dung beetle, the volatiles associated with feces is a good indication of the location of that food source. For European kestrels, studies have indicated that they can see the reflectance in the ultraviolet spectrum from urine trails left behind by mice. They can then follow those trails to the location of the mice to increase their feeding efficiency. We talked earlier about the way bats can eavesdrop on frog vocalizations to locate frog as prey items. And when you're feeding on cryptic prey that is using camouflage as a primary means of reducing predation, one of the things from the predator's point of view that increases predator efficiency is to develop a search image. So studies of blue jays, European blackbirds have indicated that using a search image increases the foraging efficiency of these species. So in the figure here, in these cryptic moths, looking for the specific pattern associated with the shape of the moth will help you increase the rate at which you can detect them on the background structures that they're sitting on. Here's some data from one of these studies. In this study, they looked at 2 cryptic species of moths, and they trained blue jays to peck at a screen when they recognized the screen had a moth in it. And the slides that were presented to the blue jays had either 1 moth or 2 moth species. And what you can see from the data here on the left, that when both species were presented, the birds never really improved their ability to find the moths in the picture. But it didn't take very many trials when just 1 species was shown to them where they could significantly increase the accuracy of being able to determine whether a moth was present or not. And it really didn't matter which species it was used in the single species trials. So in both cases, the shape of these curves is the same. So with 1 species, they were able to form a search image, but if you had 2 species in there, they weren't able to actually develop that search image, and so were not able to use that to improve the efficiency of finding this cryptic prey. Now, one of the things we've talked previously about some of the benefits of being in a group to avoid predation, but being in a group as a predator or as something that is trying to find a food source, that can be beneficial as well. This is particularly true when finding the food source is the issue. The food may not be that limiting at some location, but the food source location varies in unpredictable ways, both in space and time. And in those circumstances, foraging in groups can be very beneficial. This idea is sometimes referred to as the information center hypothesis. And the colony or the roosting location of animals is the information center itself. And how it works is individuals at the colony wake up in the morning, for example, and they're going to go out and try to find food, and all of the individuals basically go in different directions looking for the food. Many of them will not be successful, but maybe one individual is successful. These individuals then return to the colony, again, some unsuccessful, some successful. The ones that notice who brought food back will then follow these individuals to the food source. And some days you may be the follower, and other days you'll be the leader. Here are some data to show support for this increasing the efficiency of foraging for all group members in a colony. This is data from osprey. Osprey sometimes nest solitarily, sometimes they nest in colonies. This is one of these situations where they nest in colonies. If you look at the data on the left, figure on the left, what it shows you is in certain circumstances, early in the morning, the birds don't know where schools of fish are at that particular time. Schools of fish move in unpredictable manners, and so from day to day their location is going to vary. So everybody goes off in different directions, and if no osprey returns with prey when they go back out again, everybody's basically just going in very different directions. There's no real clear pattern here. However, in circumstances where an individual does come back with a fish, in this case an alewife, you see that there's a strong directional pattern associated with the other colony members. They will then follow this successful individual to this school of fish. The figure on the right shows that this does significantly increase the effectiveness of fishing. If you look at the number of birds and the time it takes them to capture an alewife, when they're naive, there's a huge range. Some of them get lucky, but many of them it takes them a huge number of minutes before they can catch a fish. But the informed osprey, ones that have followed a successful individual back to a hot fishing location, all of them are able to catch a fish in a much more reasonable period of time. Sometimes this is also referred to as mutual parasitism. Perhaps there is some cost to these leaders by the leaders going to this food source. Maybe there is a little bit of an additional competition for the resources at the food site, and so it may at that instant reduce the efficiency at which they can catch a food item. But remember, and this is kind of where the name comes from, mutual parasitism, you may be slightly harmed by leading others to a food source one day, but the next day there's no guarantee that you're going to be able to find the food, and you can rely on some other individual in your colony finding the food. In that situation, you benefit from that knowledge, and so in the end it works out for the benefit of all. And there's some other potential benefits of the information center hypothesis and the potential for leading individuals back to a food source. We talked about how foraging in groups has anti-predator benefits. So the dilution effect, birds that, gulls for example, that find a food source and lead other gulls to this food source may suffer lower predation rates. By benefiting from the dilution effect, the chance that you are killed by a potential predator is reduced in these circumstances. And also there's better detection of potential predators. So these are some of the things we talked about previously. One of the species that has been demonstrated and put in the context of the information center hypothesis are honeybees. Honeybees basically wake up in the morning, they fly in different directions, kind of scoping out the floral resources and which ones are at kind of maximal production at any given day. And they have the ability to come back, and instead of just relying on individuals then following them back to that food source, they have evolved a communication system to indicate the quality and direction of a food resource. And they do this by a couple of different dance displays. One is called the round dance, one is called the waggle dance. And the round dance is a fairly simple behavior where they basically just go enter the hive, and on the comb itself they run in big circle patterns. And in that situation, they're basically giving off the scent of the floral resource that they've just returned from, but they're also indicating, hey, look, I found this, and it's pretty darn close. So don't even bother, trying to get some indication of the direction. It's within 50 meters. Just go, go, go. Go find it. The waggle dance, however, which is shown here on the right, is far more elaborate and actually contains far more information. The bees basically end up doing a round dance-like behavior, but at one point they do this vibration, this waggle, this vibration, and that indicates that the resource is farther than 50 meters, and the more intense the buzzing, the closer it is, just past 50 meters, for example. If they just do a little bit of wagging, that means it's much farther away. And the angle that this is off of vertical from the sense of gravity, that angle is also the angle in degrees away from the sun as you exit the colony. And so that tells them which direction to fly. So the waggle dance has both distance and directional information. And here is a video that demonstrates bees actually doing the waggle dance.
Aroma and taste of the sample are alluring, but how far and in which direction is the source of the sample located? Whoever can read the language of bees will immediately understand a clear answer through a bee dance. This time, the simple round dance is increased to an elaborate minuet. The dancer is walking again and again in one direction, wagging its tail. Similar to a compass, the straight line indicates the direction in relation to the sun in which the fellow bees have to fly. The number and duration of tail wagging is a code to indicate the distance from the colony. If one follows and copies the direction and swing of the dance, she will learn the correct location.
Now, there have been some pretty ingenious experiments to demonstrate how effective the round and waggle dance, in this case the waggle dance, is in indicating the direction and distance associated with a resource. So let's look at directionality first. So with a hive in a set location, they trained bees to find a food resource, which was basically a platter full of nectar at F. Once individuals had been trained to that, when they flew back to the hive, then researchers opened up comparable nectar resources, platters of sugar water basically, spread out at equal distances but different directions from the hive. Some fairly close to the direction of one directly in line with the original training resource F, and others at varying degrees of different directions. And then what they saw is, in subsequent visits, how many bees found each of these new platters. And as you can see from the numbers indicated by each of the dots, the one that's in direct line with F received by far more visitation, indicating that the individual that first found that, the scout bee that found that, was indicating to its hive mates the location of that, directional location of that resource. And that as you get farther and farther away from that, you have fewer and fewer bees finding resources that are of comparable value. Similar experimental design in B here, but in this case, they trained them to visit a feeding station that was 750 meters away from the hive, and then in that straight line, they put out, again, comparable resources at different distances ranging from under 200 meters to over 2,500 meters. and looked at recruits to each of these equally rewarding feeding stations. And again, what you can see is that in the short period of time once they provided these resources, the two closest to the training feeder site received more recruits, and that as you got farther and farther away from this, you had fewer and fewer hive mates finding that. Again, indicating that the original scout bees that found the training station were indicating the distance, the appropriate distance to this resource. And despite the fact that there were closer resources, most of the bees were just completely bypassing this to go and search in the localized area from which they had received information from the scout bee. So we've talked about how you can find a food item. Well, one of the things that you can do is also attract prey to you by using deceit. We talked about this when we were talking about communication. Basically be an illegitimate signaler. So we gave the example of the anglerfish and the lure to attract prey to the area. Here's another example of this. The bolus spider hangs and dangles this sticky ball on a web that mimics insect pheromones that they swing back and forth, that attracts insects that get stuck onto the ball, and then they reel it in to eat the prey. Another example, golden orb weaving spiders actually produce webs that have a yellow sheen to them, and this sheen matches the yellow coloration of pollen that is an attractant for stingless bees. And so the stingless bees come to investigate this web because of its coloration and get caught as prey. So basically exploiting this sensitivity that the bees have for this coloration. Other orb weaving spiders make webs that absorb ultraviolet light. What this does is it makes these webs less visible, and the idea here is that perhaps insects are more likely just to be normally flying by this area, not see it, hit the web, and get stuck. So you're not actually trying to attract them to the area, you're trying to be invisible and just hope that they come by. This is basically the terrestrial version of filter feeding you see in some aquatic organisms. There is a third strategy that some spiders use. Some spiders, orb weaving spiders, put these zigzag designs in their web. And there are a variety of hypotheses that have been put forth to try to explain this behavior. One hypothesis is that it's basically to keep non-prey from crashing into the web. Things like you and me. As we're walking through the forest, if you see this, you're going to avoid it. You're going to step around it instead of crashing through it and ruining the web, because webs take a lot of time and resources for the spiders to produce. They're designed to capture prey. Larger things crashing through them just ruin that whole tactic. And in one study, decorated webs did have a 45% lower damage rate than undecorated webs. So there is some support for this hypothesis. A second hypothesis is that this may make the spider look larger and scarier. Oftentimes when you see the spider in the very center of this, the spider is putting its appendages right in this decorated part of the web. Go back and show that. Here you can see that kind of makes this spider look bigger, in which case it might be more frightening, and it could scare off something that would be interested in finding spiders to eat spiders. Well, in one study that tested this hypothesis, they actually found exactly the opposite. This is what we call a Y-maze experiment, where you put an organism you're testing for their preference in one kind of the base of the Y, and then you give them the choice of two hallways to walk down depending on what their preference is. And at the tips of each of these ends of the Y, they had a web that was either decorated or one that was undecorated with a spider associated with each one. praying mantis, they eat some of these spiders, and what you can see is the praying mantis was actually attracted to the web that has the decoration more than the undecorated one. So it didn't have the effect of scaring off at least a praying mantis. In fact, it actually made it more likely that the mantis would use the decoration to find the spiders. There is a third hypothesis, though, and it gets back to the luring idea, using deceit. Garden spiders with web patterns sometimes attract more pollinating insects. And here's an ingenious study that demonstrated this. They took wire hoops and they had spiders build webs on these hoops. Once the web was built, and these are spiders that normally make these intricate central designs, they took half of the hoop and removed the webbing. In one case, they removed, and then on the part of the web that had webbing left over, in some cases they left the design in that side of the web. In other cases, they removed it, but they left the design in the other part of the web that doesn't have what normally would be a webbing, but they've taken the web out. Okay, now the idea for this is that the one on the right that has the design in the side with the webbing retained, that's attracting those insects to the area that has webbing, and so that should be maximally effective at capturing prey. On the far left, where there's actually just webbing and no potential lure with the design, you would expect if the lure is really having an effect that you would have much lower capture rates here. Now the center is basically kind of an intermediate in expectation. You have the lure, it's just in the wrong place, so you may not capture as much as you would when the lure is in the right part of the web, but you're going to capture more than the web that doesn't have a lure at all. And that is exactly the pattern that you see. Where you have the lure in the right part of the web, that's where they caught the most insects, and least in the cases where there was no webbing, and then where the no design, and then where you do have the ornament design, but in the wrong part of the web, that's where you have intermediate captures. Now, when it comes to capturing prey, sometimes working in groups is beneficial to not only finding the prey, but actually capturing it, the prey itself. So, pelicans and whales are examples of organisms that will coordinate their actions to increase the rate at which they can capture prey items, in this case fish. So they'll basically kind of force, their coordinated actions will force fish into tighter schools that they can then attack. Sometimes working in groups can allow you to catch larger prey than you would have been able to do on your own. So lions, wolves, hyenas work in these coordinated groups to take down really large prey items, much larger than an individual would be able to successfully capture. In this cases, prey that range 6 to 12 times the individual weight of the predator. Similar result was found in social spiders that build webs in close association, sometimes sharing parts of the webbing together. What they did in this study was look at the size of the prey captured when the prey strikes a net, a web, just one time, and then what happens when an insect hits the web but ricochets off and ends up getting caught in another one. And if you look at the distribution of these two, when it hits the web for the first time, the black bars, you can see that distribution is shifted to the left compared to the ricochet web. So you very rarely catch large prey items on the first hit, but oftentimes you will catch a very large prey item on the ricocheted web. And so by building in close association, sometimes you will benefit by the location of another individual's web. Okay, to review. First of all, we talked about how organisms can locate food, and the cues to the food location can vary. Sometimes it's odor, sometimes it's sight, sometimes it's sound. And when you're searching for cryptic prey, search images can increase your efficiency in finding that prey. We talked about the benefits of social living and finding prey items that are unpredictable in time and space. That's associated with the information center hypothesis. Individuals will change their roles from day to day, being the individual that either finds the food or is as a follower, but it works out in the long term for everybody in the group, despite the fact that on a specific day you may have reduced foraging efficiency by individuals following you to that food resource that you found. And so in that regard, sometimes it's referred to as mutual parasitism. And lastly, in regard to the information center hypothesis, we talked about how honeybee foraging takes this one step further. There is definitely the hive is an information center, but individuals don't just follow successfully foraging individuals to the location of that resource, but the honeybees have evolved the ability to communicate the location and both direction and distance using a waggle dance, and a simpler version of it, the round dance, that just says, here's a food resource that's fairly close. We also talked about how to attract prey by deceit, by using lures or web coloration and ornaments in the case of spiders, and these are examples of illegitimate signals. And lastly, we talked about prey capture associated with another benefit of working in groups. Groups can coordinate their behaviors so that they can capture more prey more efficiently, or in some cases capture larger prey than individuals would have been able to do on their own.